Hello guys, welcome to this tutorial series on EMV. My name is Derek Peng Yu and I'm a hardware software engineer. Today I will be talking about EMV's answer to reset, in short ATR. First we will see two types of EMV reset and how they are triggered. Next we shall talk about some specifics about the clock frequency to use and how to calculate the baud rate. After that we are going to talk about the format of the ATR, the EMV is expected to send, and the meaning of each byte as defined by the specification. Next up, we will go to a demo session where I will use different bank cards and show you how their ATRs look like. Code reset occurs at power up. A terminal is expected by the specification to perform a code reset when a card is inserted during a session. The terminal is also expected to provide power to the EMV card at first, and then a stable clock signal with frequency between 1 to 5 MHz will be applied after maximum 20 milliseconds. The reset signal, which per default is low, will be set latest after 45,000 clock cycles to high. The EMV card will reply with an ATR. Warm reset is similar to a cold reset, but the card is already warm. That means the card already had power, clock signal, and code reset was already performed on the card. So warm reset is just the second try of a terminal to get the ATR. In that case, the reset signal is first set to low, and after about 45,000 clock cycles, the reset signal is set back to high. Thereafter, the EMV card is expected to respond with the ATR. Now let's talk a bit about some basic important attributes associated in implementing an EMV terminal, which are also related to the answer to reset. The frequency and the baud rate must always correspond to have a successful EMV terminal. The baud rate is the inverse of the bit duration. A bit duration is called the elementary time unit. The elementary time unit is calculated as thus. Fi and Di can take different values but are per default 372 and 1 respectively. So therefore, designing a terminal will require you to decide on a baud rate with a corresponding frequency in the accepted range. My design uses 9,600 bits per second, which implies that my frequency will be 3.5712 MHz. One of the reasons of the ATR is, for example, to exchange parameters of Fi and Di, which may have these different possible values, but the default value, as you can see here, for Di is 1 and for Fi is 372 for a maximum frequency of 5 MHz. You will also ask, what if Fi and Di in the ATR of a card don't correspond? The answer is simple. EMV also specifies that a terminal can negotiate those values with a card. So in most cases, the card will always accept default values, which makes it easier to be implemented without trying to change either the frequency or the baud rate at runtime. Now let's talk a bit about some basic important attributes associated in implementing an EMV terminal. TS is the initial character. It is either 3F for inverse convention or 3B for direct convention. Inverse convention just uses the opposite of direct. E.g., for inverse, a logical 1 is considered as low and high is a logical 0. Bits and bytes are also transmitted inversely, so they begin at the most significant bit or the most significant byte, and vice versa for a direct convention. T0 is the format character. It comprises of two parts, two nibbles. The most significant nibble from bit 5 to bit 8 is used to indicate the presence of TA1 to TD1, this byte here. Logic 1 indicates present and 0 absent. The least significant nibble, that is from bit 1 to bit 4, indicates the number of optional historical bytes present. TA1 to TC3 or to TC1, sorry, are the interface characters. They convey information that shall be used during exchanges between the terminal and the ICC subsequent to the answer to reset. So all these characters are the interface characters, but with different meanings as we go on. TA1 provides FI and DI used to determine the baud rate or the frequency. So we saw here that FI and DI are being used to calculate the ETU, that is the elementary time unit, which also needed to calculate the baud rate. So TB1 is deprecated, but it represents the voltage requirements. It conveys the values of PI1 and 2. PI1 is specified in bits B1 to B5 and is used to determine the value of the programming voltage. PI2 is specified in bit 6 to bit 7 and determines the maximum programming current. Bit 8 is not used and is always set to 0 if present. TC1 is the extra delay between bytes required by EMV cards. If it is 256, that is FF byte, it means 12 elementary time unit will be used for protocol T0 and 11 ETU for protocol T1. TD1 indicates the present. TD1 indicates the presence of subsequent interfaces, that is TA2 to TC2, these three interfaces, and also the protocol type. So it's very similar to TD2 and TD3, as we shall see. So TA2 indicates whether an EMV card will operate in specific mode or negotiable modes, respectively, following the ATR. So the bit 8 defines if mode is negotiable or not. If bit 8 is 1, then the mode is negotiable. If not, then only a specific mode can be used by a terminal during transaction with an EMV card. Bits 1 to 4 of TA2 indicate the protocol to be used in a specific mode. The absence of TA2 also indicates a negotiable mode. TB2 is similar to TB1 and also deprecated. TC2 is the maximum waiting time for protocol T0. I will make a video on protocols supported by EMV card, but for now let's just keep it simple. TD2 indicates the presence of subsequent interfaces TA3 to TC3. These are interfaces used mostly for protocol T1, and I will explain them when I make a video on the other protocols. TI represent the historical bytes, which indicates operating characteristics. And TCK is the check character to determine if there was an error during transmission of ATR. And TCK is calculated using XOR of bytes T0 to TCK. Okay, let's move over to a demo session and I'll show you how I implemented those bytes and use them to get ATR, and then I'll show you a function how to parse the ATR. Okay, this is the variable that I use to save my different attributes in the ATR. So we're going to take a quick look at the structure. That it should be the ATR. And in the ATR, you see I got different variables. I have the initial character, which is the TS, and then the format character, which is the T0. And I have here an array of interface bytes. And if we go into the interface bytes, here, where are they? Interface bytes. So right up here, so I have the TA, TB, TC, and the TD. So for the valid mask, it's another variable that I just added to be able to know which one of them is valid. Okay, and then I have the historical bytes and the historical length. Remember, the historical length can be gotten from the T0 byte, that is the format character, and the TCK is the check byte that is used to check against any error that occurred during transfer from the card to the terminal. And then I use this to check if the TCK byte was sent, and this is to save the number of protocols, and the negotiable variable is used to know if the ATR or the card has a negotiable mode, and so on. Okay, let me not take much of your time and then just go ahead and run it. First, we're going to take a look at my code reset function. What I do here is simple. I set the power to 1. This is the power signal. And then I delay for about 20 milliseconds. Then I start my terminal. And then I provide a stable clock here. And then the specification specifies a maximum of 45,000 clock cycles within which the reset signal has to set back to 1. Has to be set back to 1. So I delay for about 43,000 clock cycles. That is like 12 milliseconds. And then I set my reset signal back to 1. And then after that, I expect to get an ATR from the card. So all this is within my initialize function, which I call in my main function. So here I do my code reset, and then after that I get the ATR from this function. Okay, I'm just going to let it run to this point. There you go. So now I've already supplied everything to trigger the code reset, and I'm going to step into this function and show you the point where I get all the ATR, and that is exactly at this line. So I'm going to put a breakpoint here, or just let it run to this point. Bam. So I got everything now in this array, receive buffer. And what is left to do next is to parse everything in my card's ATR variable. So you can see here that I have the initial character, the 3B, and that is the direct convention. And then I have the format character, and then I have the interface bytes, and so on. And I think this one is just the check byte. Okay, I'm gonna let it run, get out of this function. This function is the parsing function. Here I get the initial character, the format character. Here I get the length of the historical bytes, which is stored in the format character. And then in this while loop, I just go around and check if the interface bytes are synced. I check this mask, and then if they're sent, I store them in the respective protocol layer. That's just what I do in this loop, and then I check if also it's a negotiable mode in the TA byte. So at the end, I get all the historical bytes installed in the array. So yeah, I'm gonna put the breakpoint here and then just let it run, and then we check the variable. Now we got everything in here, and yeah, you see the initial bytes, the format character, the interface bytes, and this is my valid mask showing all these bytes are valid because they are all 111. And for the second one, only the TD byte is valid. The third, only we have two, that is A and B, are valid bytes, and then we have a historical byte. We don't have any historical byte. Okay, the historical byte length is 15, but the historical bytes are all 0. Okay, that's strange. Yeah, anyway, that is how it goes. Let me try another card, and then we'll see the differences. I'm gonna switch the cards now in the card slot. Then I reset it, and I let it run again. Okay, so what do we have here? We have the initial character, the format character. We have a historical byte length of 15 and the check byte here. We also see here that this one is negotiable, and it has a protocol of T1. And what else can we get from here? Let's check the interface bytes. You see different interface bytes. This one signifies the FI and the DI values. So from here you can determine the frequency which the card is supporting. And then what else can we derive from here? Our valid mask is showing that all these four interface bytes are valid. This one is showing us that only the TD byte is valid, and the next one showing us that the TA and the TBs are also valid. And for this one, yeah, we got some historical bytes. So you see they differ according to the CAD issuers. So they can use it. I don't know exactly what they use this one for, but they mostly use it for proprietary purposes since it's not defined in the specification. Okay. Let me try another card. I'm gonna try a backlit card now, and we see. I'm gonna reset it, and I let it run again. Okay. Okay, now we have the direct convention, the format byte, the interface byte. This doesn't seem to be updated. Okay, it looks okay. Yeah, it really looks similar to the other card that I just took out. Yeah, okay, but these bytes are different now. And then let's check if it has some historical bytes too. Yeah, it has. So the last two cards kind of look similar, but differ in some few bytes. Yeah. So you see, most of them have similar values in TA and in this TA bytes. That is for the frequency. Let's try to decode it and see what happens. For the TA byte, it is the first four Least significant bits, that's bit 1 to bit 4, give the value of di, and that is 6 in this case. 6 will be 32, and then 9 indicates the fi byte, which gives the value 5. So we'll have a value of 32 divided by 5. That would give us 32 divided by 5, 6.4. 6.4 divided by 3.571200. No, 3571200. And then the inverse, we have a baud rate of about 558,000 beats per second. That doesn't really make sense. I think I made a mistake between my calculations. So the DI bit is from bit 1 to 4. That is 6. And 6 here is 32. The FI bit is 9. That is 512. Okay, that was my mistake. So instead we're gonna have 512 divided by 32 gives us 16, and then we divide it by the frequency in hertz. That should be 3571200. And then the inverse, we have a baud rate of 223,200 beats per second. Okay, this one makes sense, but it doesn't mean that you always have to implement a system where you have to always change your clock and your baud rate. And that is why EMV specifies this negotiable mode. And in this case, this one is negotiable. This is it. So it means I'm just gonna send a negotiable sequence to let it know that I want to use the default frequency and the default baud rate, and that should be it. It's gonna accept it, and that is why it's easier than to implement the terminal. Okay. Yeah, that's all about ATR. If you have any more questions, just drop a comment and I'll be happy to give some more explanation. Thank you.